Okay, so start with that. What I would like also to say is, just to keep it in mind, as we move to magnetostatics and then transmission lines and so forth, a lot of these topics will get you on one step at a time. You start accumulating a lot of topics together. And what I would like to suggest that is you try to be in class as much as possible, as opposed to listening to the videos, which are there only to provide help, not necessarily to replace the lectures, or to listen online, all right? It does not have the same kind of thing. This is a face-to-face class, and I do it synchronously online because of COVID and to help those who really needed to be at home. But I have to say, you're gonna miss a lot by not being in class. And that is gonna be a problem that you can, that eventually, you know, by missing a lot, being only online, then your problems will accumulate. Not too many students come to office hours. I'm trying to have office hours 3 times a week, times 2, 6 hours, all right? On Monday, nobody shows up. On Wednesday, so I was trying to think when to put the Monday office hours. On Wednesday, very few people come. And on Sunday, more people come but to solve the homework, but by then it's already late. So, the other thing, some students have asked me to meet with me separately, which I appreciate and I would like to do my best, but I cannot. I have so many requests because somehow all of these office hours provide conflicts, and I just cannot meet everybody else's schedule. That's not possible. So please utilize your office hours. If you have a consistent problem with your office hours, with exception, well, I don't know why you would have it on Sunday, but in any case, if you have other classes during Monday or Wednesday, or Friday we don't because nobody shows up either. So I have to reconsider how I'm gonna, what time I'm gonna put my office hours. But I think many students are not using the office hours. Many students do not show up in person for these lectures. And I think you're going to be surprised if many students don't do well. And I don't know how to help you after that. When you realize that you're far behind, it's going to be too late. And so please keep that in mind. That's all that I wanted to say, because you're free to choose whether you want to come to class, whether you want to come in person, take it, it's all your choice. But I'm telling you, I try to inform you so you make the right choices for yourselves. Okay, so what we have seen, and I will draw here, so to see it, to just draw a few things and try to summarize with what we have seen so far in terms of forces. We have seen that if we have a charge that is stationary, all right, is here, then this charge creates an electric field. And then if it's a positive charge, as I show here, it creates an electric field that goes like that. And according to Coulomb's law, this electric field, as you move away from the charge, it changes as 1 over r squared, all right, as you move away from the charge. Okay, nothing else is created in the presence of a stationary charge. And of course, how we introduced the concept of the electric field, we did it from the concept of the electric force, if you remember. And we said that the electric force is nothing else but QE. So for example, what does that say? That if in the presence of this capital Q charge, I bring another one charge, Q, All right, then this charge, if it's positive, is gonna feel a repulsive force. If it's negative, it's gonna feel an attractive force. If it's negative. However, and I would say the force on this charge is expressed as the product, the scalar product between the charge itself and the electric field that is exerted because of the charge capital Q. All right, so the way we here, we introduce it through the field, but the way we introduced it in the beginning was through the force, because the force is what we experience. All right, so we went from force, electrostatic force to the electrostatic field. But now that we have all felt comfortable with the concept of the field, electrostatic field, then practically the best way to express the concept of the field and the force is like the way I have presented it. But so now, in any case, we have, therefore, a stationary charge Q that exerts a force F sub E to any other stationary charge that is in the vicinity. All right? What happens if this charge Q, so this is electrostatics here. Let me write it. What happens if this charge Q now moves? All right, and we have here, for example, that we have a charge Q or capital Q. So let me follow the previous one. That is moving with a velocity v. All right. What is this gonna do to any other charge that is coming close to it? This other charge is going to feel an additional force. So because of this, because of the charge moving with a velocity v, which is constant here, another charge in this position Q will feel an additional force. So now that the charge is going to have the forces that you feel in this particular case because of the moving charge have two parts. You move the original electrostatic force because of the charge itself, plus an additional term because of the movement of the charge. Okay, and so instead of having this equation here on charge Q, we are going to have a different equation here on charge Q, which is going to be the original F sub E, all right, that we have Q E, sorry, Q, I should say, Q E, where E is the electrostatic field because of Q, plus F sub M. And F sub M in this case, as you can see here, is of course the charge Q, all right? This is the charge that feels the force, and is the velocity of this cross another field which is defined by this relationship, all right, B. So we have now that a moving charge creates two types of fields, all right? So a static charge creates only one, which is the electrostatic. A moving charge creates an additional one, which is called magnetostatic. all right? And this moving charge is with a constant velocity v. And so this magnetostatic force then is expressed in terms of a new field. So now the way to think about this new situation is that a static charge creates only one field, the electrostatic. A moving charge creates two fields, the electrostatic and the magnetostatic, all right? And usually the sum of the two forces is what a charge who is coming in the vicinity is gonna feel. Now, we go from there, all right? So maybe we need to, before we go any further, we need also to say the following. If I have an already excited magnetostatic field by another moving charge, and then I place in there a wire because of, so the wire may have charges in there, all right? A wire with a current has a charge that is moving with a constant velocity. So in this particular case, what is going to happen is that your charges in the wire, that they move with a constant velocity, they feel a force. And this force is going to be the total force, of course, all right? But because this one charge, if we assume that I would say that the wire is flexible, this force is going to move the wire. It's going to try to move the charges, and with that, the wire. All right? If the wire is not fixed, but is a soft wire, then, and the force is strong enough, that meaning B is strong enough, then practically this wire is going to move. And how does it move? Now, using this different, not different, I mean, it's a derivation of the previous formula, but it shows that if there is a current flowing through a wire in a strong magnetic field, then this magnetic force that exerts on each of the charges is going to move the wire, and the force is characterized by that. So, what to summarize everything. You have a static charge, it's not moving. You bring another charge, there is a force. There's a force in between them, all right? If they are of the same polarity, it's gonna move them away. If the big charge is here, the small charge is gonna move away. And if they're of the same polarity, they're gonna come towards each other. If you have a moving charge that creates a magnetic field, and you put another charge, then this charge is gonna feel an additional force coming from the magnetic field. And if, in fact, the charge moves along a particular direction and creates a current, all right, then this current here is a current filament. So you can think it's not just charges in free space, all right, but they're charges that are conducting through a particular conductor, obviously. In this particular case, the conductor is going to feel this force, which in fact is going to be only due to the strong magnetic field, and it's going to come out of this expression. All right. Now, what you're going to see here, we have assumed that we have only one strong magnetic field. We have not assumed that we have an electrostatic field at all. All right. So while we have generalized this formula for cases where there is both an electrostatic and magnetostatic field, in this particular case, in this particular example, we assume that the electrostatic field does not exist. All right, we somehow created only a magnetostatic field. Yes. Yes. When, for example, you have charges that flow around in a closed loop, then you only have a magnetic field. when you have charges that moving back and forth. So if you have charges moving with a constant velocity, you will only have a magnetic field. When you have charges that move with an acceleration, you will have both. When you have static charges, let's assume that you are in a space, all right, where you can have the two, they're coming from two separate sources. So that's possible. Let's assume that I have a sitting charge here, and then I have a wire here with a current. This one creates a static field. This one creates an electrostatic field. This one creates a magnetostatic field, the wire. And if I bring a new charge in that space, then it will see both. It will feel both fields, all right? So yes, it is possible to have both, but they may not necessarily come from the same source. They come from separate sources, the electrostatic and magnetostatic. So far, they may come from different sources, or they may come from the same source. And what are the conditions of coming from different sources? What are the conditions of coming from the same source? All right, let's clarify that. If you have a static charge only, that's going to create only an electrostatic field. If you have a charge that is moving with a constant velocity, this is going to create only a magnetostatic field. So if you bring those two charges close to each other, you're going to have two separate fields, but they're not going to interact. But if you have a charge that moves with a variable velocity, so accelerates, decelerates, then that charge, which is going to be one source, obviously, is going to create both electric and magnetic fields. Okay, that's how it is in physics. So here it shows what happens when you have an electrostatic and magnetostatic field. And we said electrostatic, only a static charge, magnetostatic, only a charge moving with a constant velocity, and maybe both if you have a charge with a varying velocity. But no matter what, if you have an electrostatic field and an electrostatic field, or an electric field and a magnetic field, just to be more general, electric field and magnetic field, then a new charge that you bring in that environment is going to feel this total force. This is true for all cases, all right? Then now we say, assume that we don't have electrostatic field, that I only have a wire that starts at some point and closes at some point, which means all the charges can move around forever, all right? Assuming that we don't have losses. So the charges move around forever in that wire with a constant velocity. So it makes a current practically. In that case, I will have only a magnetostatic field. And in that particular case, if in this magnetostatic field, I bring another wire that has another current, then this new wire is going to feel a force. Let's give it like that. The cross product between the wire itself that now I brought into the magnetostatic field, cross product with the magnetostatic field, all right? So we have introduced these two separate concepts. And from here, from the what we call, this is called, in fact, because it's so general, it's called the electromagnetic force that includes both electric and magnetic, the top one. And also is known as the Lorentz force. All right, so the Lorentz force includes both electric and magnetic, either static or electromagnetic. This one is called only the magnetic force, and this is what we are going to use from this point on. We are going to use this one to start studying phenomena within magnetostatic fields, within fields that are only magnetic, but static magnetic. What does it mean, static magnetic? They do not change with time, all right? Static electric means it does not change with time. That's all it means. It changes with space, obviously, but not with time. So we are going to start then looking at these types of fields. And here is an example. You see, I told you about charges that move around with a constant velocity. This is here an example of that, where you have a wire and there is a current in there. Now, obviously, this is theoretical, all right, the representation, because you cannot support a current in a wire without having a source somewhere. We're going to come to that, but assume that you have a source somewhere, and then you are creating, you sustain this flow of charges with a constant velocity. That's what current is, all right? The current is charges flowing with a constant velocity, okay? If you have that, then you create a magnetostatic field. And as a matter of fact, as we will see, inside this, not everywhere, but if you were this electrostatic field, the green one is coming from another source, obviously. It's not coming from that wire. But if you bring this wire inside the magnetostatic field B that is created by another source, then this wire is going to feel a force. And the total force, because now is the wire, okay, so the current in this wire, the charges in this wire, rather, they feel this force here, but because they run across the whole circle, then you will have to integrate. All right? So practically, if I were to be correct, what I would have to say is that here, when I have a this relationship here, it's most accurately written in this form, which says, because this assumes that you have a current that goes straight in a magnetic field that goes straight, all right, and then you get that. But in reality, we know that we are not constrained into these very theoretical structures, an infinite wire going like that, and an infinite magnetic field going like this, all right, the other direction. It's not happening like that. Usually, we have a wire that may have whatever shape. We have, therefore, a current in this wire might be constant, but because the wire changes, all right, shape, so obviously the current as a vector is going to change shape. Because the current has the value the same. If you have a current in a wire, like it's here, this current in the wire as an amplitude is constant, all right? Because, you know, it's the same number of charges moving around with the same velocity. Nothing changes. So the current in this wire is the same wherever you go. The direction of this current is different. So the current as a vector here changes, all right? And that's why we write it in this form, which says that if I take an infinitesimally small section of this now, a current that has a direction with it, then this infinitesimally small section of the wire here, if we assume that this is, I may make it red, this infinitesimally small section of the wire there, or the current, is going to feel this infinitesimally small force, all right? Because of this B field that exists there, which means to find the total force applied on this current, then you have to integrate around the path the current takes, which is the circle, all right? So did you understand how we go from here there? Is that clear? All right. So that says it even better. Okay, so now let's go here and again repeat what we've heard. What we've heard before, and I will write it here, is that if I have, so I'm just saying, repeat what we had before, that if we have an infinitesimal section of this wire, and I take an infinitesimal because it changes, you see direction, the current remains the same, but it's going on a path that changes. It's not a straight path. Then that's why as a vector, it changes. just because it's, so the current as a vector, the current changes just because its direction changes. So I have a infinitesimal part of this current, and this inside a magnetic field, as we said before, is gonna feel a force. Okay. So now from there, we go and say the following. If this current in presence of the magnetic field feels a force, then that makes me assume, which is correct, that the current by itself creates a magnetic field, all right? The current would not feel a force. I mean, the wire, when the current flows, would not feel a force if there was no current. All right, so if I have a magnetic field and a wire without current, this wire, the mass of the wire is not going to feel any force. The wire starts feeling a force the moment there is a current flowing into it. And why does it feel this force? Because by itself, this current introduces a new magnetic field, all right, which is then works against the other magnetic field. And that's why the force is in place, all right? As any system, when you disrupt it, it has to go back to equilibrium, all right? You know that in every system in nature, which is in equilibrium. The moment you disrupt it with something, it's going to work itself in a way to go back to equilibrium. So if you have a steady magnetic field and nothing happens, let's assume that there is a magnet somewhere outside of here. And then so we all are under a magnetic field, which is, we are, in fact, the Earth's magnetic field, but in any case, not very strong. So we are under a magnetic field. And now we bring a wire, all right, here. Let's assume a strong magnetic field. Nothing happens to it. The magnetic field stays the way it was. Okay. The moment I put a battery in this wire, and let's assume that I put a strong voltage, and there is a strong current that flows in the wire, what happens? Immediately there is a disruption in the system, because this wire now that runs with a strong current is going to create its own magnetic field that's going to work against the previous magnetic field. So the whole system, if we let it free, is going to exert forces that eventually will pull the two sources together, or they're going to pull them apart. So the system tries again to go back into equilibrium. That's why you have these forces that they are exerted, all right? Forces create change, as you know. And change happens when you disturb the equilibrium of a system. So what we said before, it then triggers that thought into us and say, therefore, when I have a current myself, that current is going to create a magnetic field. All right? It's not only that it's going to feel the force because of another magnetic field, it's going to feel the force because of another magnetic field, because it on its own creates a magnetic field. And therefore the question is, what is the magnetic field that this current creates? And is given by, for an infinitesimally small current, is given by this. All right, so now we have an equation that tells us that if we have a current I, but over a short section of a wire, all right, because that on that short section, the current has a particular direction, then this current, which is like I times delta L, this current then exerts or creates a field, a magnetic field, magnetostatic in this particular case, which is given by that. And this is a formula that we're going to use extensively from this point on. All right. So what is the interesting concept here? that we see that reminds us of something that we have seen before. It's like that the magnetic field generated, the magnetostatic field generated from a constant current now, it varies as I move away from this current as 1 over the distance squared. Very similar to what we saw for electrostatic fields, all right? The only difference is that 4 pi, of course, in the denominator, but there is no epsilon here. See? Only that, without an epsilon in there. There is no material, any constant, material constant here that changes this problem. Okay, that's important to remember. So at this moment, I will say that what I would like to do is move for a second from here to this one, because this one shows us the specific equations that we have duality somehow between electrostatic and magnetostatic case. Sorry. I like this table because it shows you the duality of the equations. So now that we have seen electrostatics, it's going to be easier to talk about magnetostatics. Let's start with the sources. What creates an electrostatic field? A stationary charge Q. All right, so this is number 1. All right, what creates a magnetostatic field? So let me put red in these ones. In fact, I will do it like this. What creates a magnetostatic field? As we said, a charge Q with a constant velocity V. Electrostatic on the left, magnetostatic on the right. Okay. Now these fields. What is interesting about the electric field? The electrostatic field gives rise to an electric flux density. The electric flux density is here. We've seen that, isn't it? And also, if this field is in a conductor, it gives rise to a conduction current, right? With sigma is the conductivity of the material. These are 2 fundamental questions, right? Both the electric flux density and the conduction current have the same direction of the electric field. One is multiplied D, which is the electric flux density, is multiplied by epsilon, the dielectric constant. The J, which is the conduction current, is multiplied the field, multiplied by sigma, which is the conductivity of the material. What did we say about perfect conductors? Sigma is infinite. So what does it mean if sigma goes to infinity? We know that J cannot go to infinity, because otherwise you're going to have infinite many amperes. Who's going to produce this many current? There is no source to produce this much, which means what? That when sigma goes to infinity, E, the electric field, has to go to 0. And when you have a number 0 times infinity, it's not defined, but it's not an infinite number, all right? So when sigma goes to infinity, perfect conductors, then we know that the electric field is 0. And that does not have a meaning inside the conductor, because all of the charges are floating on the surface. Inside the conductor, there is none. Okay. Now let's go to magnetostatic fields. Now we introduce a new entity, which we call the magnetic flux density. And now the magnetic flux density is very similar to the electric flux density and its relationship to the electric field. Epsilon here we have mu. So the magnetic flux density is this new constant, which we call the permeability, the magnetic permeability of the material. And this magnetic permeability is also mu sub r times mu sub naught. All right. As we found that epsilon here was epsilon sub r epsilon naught. All right, and for magnetic materials, mu sub r is very large. For air, free space, mu sub r is 1. Mu sub r is 1. For the electric materials, epsilon sub r has a number, right? 2, 3, 4, whatever. For free space, epsilon sub r is 1. So we remember that. Epsilon sub naught and mu sub naught are given numbers, and you can find them on any book. They are the same numbers, and we have found them from measurements, all right? And we use that to characterize the space. Okay, now let's go to the left side because we have seen those equations. We now go, this is all for electrostatics, is a review practically of all the laws. So Gauss's law, remember Gauss's law? It's this one. Gauss's law says that the divergence of D at any point in space is equal, so this is a differential relations. Differential means at one point in space, right? Not more than 1 point. At that point, at 1 point in space, the divergence of D, which is the electric flux density, is equal to the charge at that point. And what happens if there is no charge at that point? How much is this? 0. If there is no charge, rho sub B is going to be 0. So on a charge, the divergence of D equals the charge, the point charge. Everywhere else where there is no charge, the divergence of D is 0. Okay? Well, we have not seen that, but that says that there, in a case like that, they, you remember what we said about the curve? That the curve shows rotation. Remember when we talked about vectors early? Okay, that's why it is important to have an understanding of the operations, of the operators. A del cross, you remember we said that? Del cross a vector. If it's not 0, it means that the vector rotates. Has that kind of direction, all right? For electrostatics, the del cross E is 0, which means in electrostatics, the field do not close lines. They go straight, all right? Remember how we have drawn the electric fields from charges? Straight lines. If they end somewhere, it's going to be another charge, not the same one. They don't come back to the same charge. They leave the charge and they go away. Okay. Keep that in mind because here we're going to see something else. In electrostatics, this is the divergence theorem. This is what the divergence theorem gives us from Gauss's law. We covered that and we use that extensively. All right. Which says then that if I take a volume where I have charges, this volume, and there are charges, then the volume integral of the divergence of D would be, according to this equation, Gauss's law, would be the volume integral of the charge that is in there. But with the divergence theorem, from the volume integral of the divergence of D, we go to a closed surface integral of D. We've seen that, all right? And we use that to solve a number of problems to find the electric field, especially problems that were, they had some kind of symmetry, spherical symmetry, cylindrical symmetry, or an infinite long plane, all right? Here we go now. Let's see what are the equivalent laws. Some of the laws, we will see them on Beer's law, we know them, right? Beer's law is the second, but let's start with the first one. Now, you remember that I told you very early that there are no magnetic charges, all right? There are no magnetic charges. The only thing that we have, the only charges that flow around are electronic charges, are electrons. There is no other charge that is moving around, all right? Only electrons can move. So how do we have magnetic fields? From moving electrons, but moving with a constant velocity. And because electrons move, and they have to go from one plane to another, but they have to come back, all right? Because electrons, they cannot keep going forever. I mean, we may say we have an infinitely long line. This is just to simplify things. Usually, when you have a current, it goes away, you have a battery, so the charges flow like that and come back, all right? You have to close. I mean, if a charge flows, they have to come back. They cannot just start at some point and then disappear, all right? The charges do not disappear. They exist. I mean, the universe has the same number of electronic charts. I mean, that it had in the beginning. It's just that it was in a different form. So the energy is like, if you say that electrons disappear, it's like you say you lose energy without having a sink of energy anywhere. All right, always energy is balanced. I mean, this is the second law of thermodynamics. You cannot violate that. So whenever you have, since we don't have magnetic charges here, therefore the divergence of B is 0 as opposed to that, all right? However, the curl of B, which B is nothing else but H with a constant, the curl of B or the curl of H is J. I could rewrite that as, for a isotropic linear and all of this material, I could rewrite this for the materials now we are talking about here in this class. For our class, you can write it like in this form, if you like, because it's a constant, all right? And a scalar constant comes in front of the operator, okay, or goes into the operator without a problem. All right, what that tells you, therefore, is that the magnetic field is rotational. What does that mean? That the magnetic field, the lines, when they start, they have to come back and close. You don't have, even when I showed you magnetic fields that go like straight lines, they're not lines that are going, that they are terminating somewhere else. They terminate back to where they start. That's the difference between electric and magnetic lines. Electric lines can start on a charge and they can end on another charge. Magnetic field lines do not start and end on different places. Wherever they start, they will end there. And that's what that says, that this field is rotational as opposed to that. All right, this one is very important. And this comes out of Ampere's law. So this is called the Ampere's law. The curl of H equals J. It's a very important law and it's called the Ampere's law. If we apply now Stoke's theorem, which is like another theorem like the divergence, it tells us that this up here, Ampere's law, it can be reduced to this form. And now we are going to try to understand what that means. Okay, now that we have introduced it, we are going to spend our time trying to understand that. Any questions so far? Okay, so the best way to understand this is by trying to solve a problem. Okay, and we are going to have the following simple problem, simplified. Obviously, we have a current, and the current is not, as I said, does not start at one point and end at another point, but this is a long current that goes from one end of the building to the other end of the building. So when I am here, it seems to me like it is a straight wire, all right, that goes like over a long distance and assume that it's straight. So I consider this conductivity. This is for our study of this problem. And I would like now this wire that has been excited at one end of the building and comes through our room, I would like to see what creates to us. And you know, we have all of these wires. These wires, if they are not shielded and they have current, what do? They all create magnetic fields. All of them. The good news is that those magnetic fields go down very fast. You remember what we said as 1/r squared for a section of the wire. All right, 1/the distance squared. However, we will see that if we have a long wire, like the ones we have for the power distribution, the wires that you see sometimes, these very thick wires up there that you have when they carry a lot of the current for power, these are like this. Those wires, of course, they started somewhere and they go and they will end somewhere, and then usually they come back through ground. You see them having that in a very high position, all right, with towers. Very thick wires, they carry a lot of current. So, and as a matter of fact, the voltage supports, because the voltage is really kilovolts up there. But in any case, they go like that. Now we want to see, why do you think they don't allow people to live underneath it? Because of this problem. If you have a house somehow, or if you have a house and somebody brings this wire over you, then you're going to be living in a very strong magnetic field. And that's not good. Nobody knows, you know, what happens eventually if you are any mass, biological mass. If you leave it within any kind of strong field for a long time, things happen. Things happen because magnetic fields move charges. All right, and if your ions, which are molecules, are under continuous force, all right, magnetic or electric, they're going to move. And that creates some problems, you know, sometimes disease, cancer, all kinds of things, all right? So you will see when they have very thick wires, they take a region underneath it. Usually they even take all of the plants away, or the trees and everything, and nobody's allowed to build there. All right, this is then a regulation by the cities and all of this. Now, okay, so we have a wire like that, we want to find the potential. In this particular case, the way to do it, because the section of the wire that we have is infinite long, we are going to use Ampere's law. You see here, Ampere's law says this one, that since this wire is infinite long, I will assume that it's cylindrically symmetric, of course, and I will assume that since it's straight, that whenever I cut a cross section, the same thing that I will see here is going to be there, all right? And the same thing that I will see if I am next to the door is going to be if I'm sitting next to the wall, for example. Okay, so then I reduce this problem to 2D. So practically then I say here the current, because it's a infinitesimally thin current, practically is not a total, I show it as a total current here, but in reality it goes to one point, all right? There is no current distribution, just one value. If I cut it here, you see a point. You see that the current goes through this point at the center of the disk, which is here. And therefore, I can write this differential relationship between the current and the magnetic field it produces, all right? Because this current produces a magnetic field. I then use Ampere's law and say, okay, then I know that happens. I know that at every point, on every cross section of this, if I go at this distance away, and then I draw this circle around it, I know that at this point, if I were to bring a charge, this charge would feel a force, especially if this charge is moving, another current, for example, right? So it will feel a force because of the field that this current is generating. That's your magnetic field. So therefore, I know from Ampere's law that this current J generates a magnetic field H. I know from Ampere's law that J generates H. So what do I do next? I go and I define this circle C And also, in this particular case, we have to take into consideration the direction of the current. And if the current goes along the positive z direction, then the direction of the circle that I will take for this integration that you will see is going to be using the right-hand rule. But before I get there, I go here and I integrate both sides of this equation on the surface S of this disk. All right, I define the surface S on this disk, which I have shaded. And the surface S is what is covered here, this disk. And then I take the surface integral on both sides. Now I use Stoke's theorem, as I told you here before. If I use Stoke's theorem, back to some time, then you move, say, the surface integral to a line integral here. And finally, from here, you are able to find, and we will continue next time, that your magnetic field is having only a phi component that moves it around the circle. All right. So far, therefore, we introduced magnetic fields from moving charges like currents. And then we saw the equations, and then we start thinking about how to solve problems and find magnetic fields from currents. All right. So we are going to review this next time quickly and then move beyond that again. We'll have a few reviews over time until we get used to the idea.